Welcome to another Deep Dive, and today we're going to be taking a look at Oganesson element 118.
Oh, Oganesson.
Yeah, you might be thinking, another element. How exciting can that be?
Right.
But trust me, this one's pretty interesting.
This one's a real rebel. Yeah.
It's a noble gas,
Yeah?
like helium, what you put in your birthday balloons,
Right.
but it breaks practically every rule in the noble gas playbook.
Yeah, what's really fascinating is that we're talking about an element that is so rare. We've only ever created a handful of atoms of it.
Really?
Yeah.
So it's at the edge of what we can even detect, let alone study.
Okay.
Okay, so let's unpack this a little bit. How do scientists even make an element like Oganesson? It's not like you can just dig it up in your backyard. Right?
You're exactly right. Oganesson is a synthetic element, which means that we have to create it in a lab.
Okay.
To do that, scientists use these really powerful particle accelerators to smash lighter atoms together at incredible speeds, hoping that they'll fuse to form something new.
So it's like a microscopic demolition derby.
Yeah.
But even with all of that technology, I'm guessing that it's not easy to create something as heavy as Oganesson.
It's incredibly challenging. Yeah. Imagine trying to hit a bullseye on a dartboard that's miles away while blindfolded, and the dartboard's moving at the speed of sound.
Oh, wow.
That's basically the level of precision and luck involved in creating Oganesson.
Really?
Yeah, it requires months of bombarding a californium target with calcium ions just to produce a few precious atoms.
Talk about a long shot. But how do they even know that they made Oganesson if it only exists for like a fraction of a second?
Yeah, that's where the detective work comes in.
Right.
So scientists can't directly observe Oganesson,
Right.
but they can track its decay chain.
Okay.
So each element decays in a specific way, emitting particles with unique energies.
Oh.
So by tracing those decay products back to their source, scientists can confirm that, hey, we actually created Oganesson.
So it's like piecing together a puzzle in reverse.
Exactly.
They see the final image and they work backwards to figure out how all the pieces fit together.
Yeah, and the story of Oganesson's discovery is full of twists and turns. There was even a false alarm back in 1999.
Oh, really?
Yeah, a lab claimed to have created it,
Uh-huh.
but unfortunately their results couldn't be replicated.
Yikes. Science can be a little bit of a roller coaster sometimes.
It certainly can.
Yeah.
But the real breakthrough came in 2002.
Okay.
When a team of Russian and American scientists, led by the element's namesake Yuri Oganesson, finally synthesized and confirmed the existence of Oganesson.
Wow.
It was a huge moment for the scientific community.
Speaking of Yuri Oganesson, this guy must be a legend in the world of super heavy elements.
He absolutely is.
Yeah.
He's dedicated his life to creating elements that most people would consider science fiction.
Yeah.
His work has helped us to understand the limits of the periodic table and the forces that hold atoms together.
So we've created this super heavy element, but it sounds incredibly unstable. Like, why is that? Why does Oganesson vanish so quickly?
Well, to understand that, you have to picture the nucleus of an atom. Imagine it like a tiny house packed with 118 rambunctious toddlers, all with the same positive charge.
That sounds like a recipe for chaos.
Exactly. Protons repel each other.
Uh-huh.
And in an element like Oganesson, with so many protons crammed into such a tiny space, those repulsive forces are immense.
Yeah.
It's like trying to keep 118 toddlers calmly sitting in a circle.
Right.
It's not going to last very long.
So that's why Oganesson undergoes radioactive decay. It's trying to, shed some of those protons and find a more stable configuration?
Precisely.
Okay.
It can do this through what's called alpha decay, where it ejects a cluster of 2 protons and 2 neutrons, or through spontaneous fission, where the nucleus literally splits in 2.
Wow. That's pretty dramatic.
Yeah.
So Oganesson is this incredibly heavy, unstable element that breaks down in a blink of an eye. Why are scientists so interested in it? What can we possibly learn from something that disappears so quickly?
That's a great question, and it leads us to one of the most fascinating aspects of Oganesson, its predicted properties.
Okay.
Even though it's so short-lived, right? We can use theoretical calculations to get these glimpses of how it might behave, and those predictions are pretty mind-blowing.
Okay. I'm officially intrigued. Tell me more. What makes Oganesson so special, even among the other super heavy elements?
Well, here's where it gets really interesting. Oganesson is predicted to be surprisingly reactive. even more so than some heavier elements that are known to be quite reactive.
Really?
Yeah, it's like this noble gas might not be so noble after all.
Wait, hold on. Aren't noble gases supposed to be like the introverts of the periodic table?
Right.
They have their full outer shell of electrons and they don't like to interact with other elements?
Exactly.
How can Oganesson be so reactive if it's a noble gas?
You're right. Typically, noble gases are very unreactive.
Okay.
But with Oganesson, something else is going on, something powerful enough to override its noble gas nature.
Okay, I'm on the edge of my seat. What is this mysterious force?
It's a consequence of Einstein's theory of relativity,
Oh, wow.
and it has a huge impact on the behavior of super heavy elements.
Okay.
It's called relativistic effects.
Relativistic effects. That sounds intense. I know a little bit about Einstein's theory of relativity, but how does it apply to an element like Oganesson?
It all comes down to the speed of Oganesson's electrons. They're zipping around the nucleus at a significant fraction of the speed of light.
Really?
Yeah, at those speeds, the rules of classical physics start to break down, and relativistic effects come into play.
So it's like Oganesson's electrons are living in this fast-forward world where the laws of physics are slightly different.
Exactly, and those relativistic effects have a profound impact on the element's behavior, including its reactivity.
So those relativistic effects are like a turbocharger for Oganesson's reactivity.
That's a good way to put it, yeah.
But I thought we were talking about noble gases.
Mhm.
Aren't they supposed to be the most stable and unreactor elements on the periodic table?
You're right, that's true for the lighter noble gases.
Uh-huh.
But Oganesson is a whole different story.
Yeah.
The relativistic effects are so strong in Oganesson
Okay.
that they actually overcome its inherent noble gas stability, making it potentially more reactive than some metals.
Wow, that completely flips my understanding of the periodic table on its head.
Yeah.
It's like the heavier elements are playing by a different set of rules.
Exactly. And here's where it gets even more interesting. Oganesson is predicted to have a positive electron affinity.
Now you're just messing with me.
I know, right?
What does that even mean? I thought noble gases hated gaining electrons.
Right.
They're content with their full outer shells.
You're right. Typically, noble gases have a neutral or even slightly negative electron affinity.
Okay.
They're happy and stable as they are.
Right.
But Oganesson, thanks to those relativistic effects, is predicted to actually release energy when it gains an electron.
So it's like Oganesson is breaking the fundamental rules of the periodic table.
Yeah.
This noble gas might actually be eager to form bonds.
That's what's so exciting.
Yeah.
It's challenging our understanding of what it means to be a noble gas.
Right.
It's almost as if Oganesson is behaving more like a halogen, you know, those elements that are just one electron away from a full outer shell and are highly reactive.
Okay, my mind is officially blown. If Oganesson can readily gain an electron, wouldn't that mean that it could form all sorts of interesting compounds?
That's the million-dollar question.
Yeah.
And while we haven't been able to directly observe any Oganesson compounds yet due to its very, very short lifespan,
Right.
theoretical calculations suggest that it could form a variety of compounds, including things like Oganesson fluorides, chlorides, and even compounds with other super heavy elements.
So it's like Oganesson is a chemical chameleon.
Yeah.
It has the potential to behave like a noble gas, a halogen, and maybe even something entirely new.
Exactly. And this makes it one of the most intriguing elements that we've ever discovered. It's pushing the boundaries of our understanding of chemistry and physics.
All right, we've established that Oganesson is a rule breaker, but we're just getting started.
Right.
We'll be back to continue our deep dive, so don't go anywhere.
Welcome back to our deep dive into the world of Oganesson.
So before we went on a short break, we were just starting to unravel the mysteries of relativistic effects. You mentioned that Oganesson's electrons are moving at a significant fraction of the speed of light.
Yeah.
That's mind-boggling. What happens to those electrons when they're traveling that fast?
Well, when electrons approach the speed of light, their mass actually increases.
Really?
Yeah, according to Einstein's theory of relativity. And this increased mass affects their orbital shape and energy levels,
Okay.
ultimately impacting how they interact with other atoms.
Okay, so the electrons get heavier, and that changes their behavior. But how does that specifically make Oganesson more reactive?
Think of it like this. Imagine the electrons in an atom as cars racing around a track.
Okay.
The heavier the car, the harder it is to control, and
Right.
the more likely it is to veer off course.
Uh-huh.
Similarly, in Oganesson, those heavier, faster electrons are less tightly bound to the nucleus
Okay.
and more likely to interact with other atoms, making the element more reactive.
That's a great analogy.
Thanks.
So those relativistic effects are like a turbocharger for Oganesson's reactivity.
Yeah, that's one way to put it.
But I thought we were talking about noble gases. Aren't they supposed to be the most stable and unreactive elements on the periodic table?
That's true for the lighter noble gases,
Right.
but Oganesson's a whole different story. The relativistic effects are so strong in Oganesson that they actually overcome its inherent noble gas stability, making it potentially more reactive than some metals.
Wow, that completely flips my understanding of the periodic table on its head.
Mhm.
It's like the heavier elements are playing by a different set of rules.
Exactly, and here's where it gets even more interesting. Oganesson is predicted to have a positive electron affinity.
Right. Now you're just messing with me.
I know, right? It's crazy.
What does that even mean? I thought noble gases hated gaining electrons.
Right.
They're content with their full outer shells, right?
You're right. Typically, noble gases have a neutral or even slightly negative electron affinity.
Uh-huh.
They're happy and stable as they are.
Right.
But Oganesson, thanks to those relativistic effects, is predicted to actually release energy when it gains an electron.
So it's like Oganesson is breaking the fundamental rules of the periodic table. This noble gas might actually be eager to form bonds.
That's what's so exciting. It's challenging our understanding of what it means to be a noble gas. It's almost as if Oganesson is behaving more like a halogen, those elements that are just one electron away from a full outer shell and are highly reactive.
Okay, my mind is officially blown. If Oganesson can readily gain an electron, wouldn't that mean that it could form all sorts of interesting compounds?
That's the million-dollar question. And while we haven't been able to directly observe any Oganesson compounds yet, due to its very short lifespan, theoretical calculations suggest that it could form a variety of compounds, including things like Oganesson fluorides, chlorides, and even compounds with other super heavy elements.
This is like Oganesson is a chemical chameleon. It has the potential to behave like a noble gas, a halogen, and maybe even something entirely new.
Exactly, and this makes it one of the most intriguing elements that we've ever discovered. It's pushing the boundaries of our understanding of chemistry and physics.
Okay, we've talked about Oganesson's surprising reactivity and its potential to form compounds. What other strange and wonderful predictions have scientists come up with for this elusive element?
Well, you might be even more surprised to hear that Oganesson is predicted to be a solid at room temperature.
Hold on, a solid noble gas. That goes against everything I thought I knew about the periodic table.
I know it's wild, but those relativistic effects are added again.
Ah,
They alter the way that electrons interact with each other, leading to a stronger attraction between Oganesson atoms.
okay.
This increased attraction could result in Oganesson having a surprisingly low melting point, making it a solid at room temperature.
So it's not just a rebel in terms of reactivity. It's also challenging our assumptions about the physical states of noble gases.
Exactly.
Are there any other mind-blowing predictions about Oganesson's properties?
There is one more that I think you'll find fascinating. Theoretical calculations suggest that Oganesson might actually be a semiconductor.
Okay, that's a new one. I thought noble gases were insulators, meaning their electrons are tightly bound and they don't conduct electricity well.
That's true for the lighter noble gases, but Oganesson once again throws us a curveball.
Okay.
Those relativistic effects cause the energy bands in the element to narrow, creating what's called a small band gap.
Okay.
Think of it like a narrow bridge that some electrons can cross,
Okay.
allowing for limited electrical conductivity under certain conditions.
So Oganesson might not be a full-blown conductor like copper, but it's not a complete insulator either.
Precisely. It's somewhere in between, occupying this fascinating middle ground between traditional insulators and conductors.
It seems like every time we learn something new about Oganesson, it challenges our fundamental understanding of the periodic table.
That's the beauty of science. New discoveries often force us to reevaluate our existing knowledge and refine our models of the world.
Okay, I'm ready for more. What other secrets does Oganesson hold? Welcome back to the deep dive. We're wrapping up our exploration of Oganesson, this element that's pushing the boundaries of the periodic table and our understanding of matter itself. It's amazing to think that just a few atoms of this element can make us rethink so much of what we thought we knew about chemistry.
It really is a testament to the power of scientific curiosity, wouldn't you say? We're driven to explore the unknown, to push the limits of what's possible, and in doing so, we often stumble upon these discoveries that challenge our most fundamental assumptions.
Absolutely. And before the break, we were discussing some of those groundbreaking predictions about Oganesson,
Mhm.
its surprising reactivity, its potential to be a solid at room temperature, and even the possibility that it might be a semiconductor.
Right, and all of this is largely due to those mind-boggling relativistic effects, which are essentially a consequence of Oganesson's electrons moving at a significant fraction of the speed of light.
It's like Oganesson's giving us a glimpse into a world where the rules of chemistry are slightly different, a world governed by the laws of relativity.
Exactly. And as we delve deeper into the realm of super heavy elements, those relativistic effects become even more pronounced, leading to truly extraordinary and unpredictable behavior.
Speaking of unpredictable behavior, we've talked about Oganesson's potential to form compounds,
Mm.
but since it's so short-lived, we haven't actually observed any of these compounds directly right.
That's right. Traditional experimental techniques are simply not feasible when you're dealing with an element that exists for mere milliseconds. But scientists are incredibly resourceful, and they're developing these innovative approaches to probe the chemistry of these elusive, super heavy elements.
Okay, I'm all ears. What kind of techniques are they using to study something that disappears in the blink of an eye?
Well, one promising approach involves trapping the decay products of super heavy elements. Remember how we talked about Oganesson's decay chain, how it breaks down into a series of lighter elements?
Yes, like a radioactive family tree.
Precisely. By trapping those decay products and studying their properties, scientists can infer information about the parent element, Oganesson. It's like piecing together a puzzle where some of the pieces are missing, but you can still get a pretty good idea of the overall picture.
That's pretty clever.
Yeah.
So by studying the children, we can learn something about the parent. Are there any other techniques that scientists are using?
Yes, there's another fascinating technique called single atom chemistry.
Single atom chemistry. That sounds incredibly precise.
It involves isolating and manipulating individual atoms of super heavy elements, allowing scientists to study their behavior at the most fundamental level.
So it's like performing chemistry experiments on the tiniest possible scale.
You got it. And this technique is opening up these incredible possibilities for understanding the chemistry of super heavy elements.
It's amazing to think that we can now study chemistry at the level of individual atoms. It's like having a microscope powerful enough to see the building blocks of matter itself.
It's truly remarkable. And these techniques are not just limited to Oganesson, they have the potential to revolutionize our understanding of the entire periodic table.
You know, this entire deep dive has really made me wonder if Oganesson is so different from the other noble gases. Does it even belong in Group 18 of the periodic table?
That's a debate that's currently raging in the scientific community. Some argue that Oganesson's predicted properties deviate so drastically from typical noble gas behavior that it should be placed elsewhere on the periodic table.
So if it were to move, where would it go? What other group would even make sense?
That's the tricky part. Some have suggested placing it in group 12 alongside zinc, cadmium, and mercury. Others believe that it might warrant an entirely new group of its own.
Wow, so Oganesson might not just be a new element. It might force us to rethink the entire organization of the periodic table.
It's a testament to the ever-evolving nature of scientific knowledge. New discoveries often challenge our most cherished models and force us to adapt and refine our understanding of the world.
And that's what makes science so exciting. It's a continuous journey of discovery, a process of constantly questioning, exploring, and pushing the boundaries of what we know.
Absolutely. And Oganesson, this elusive, enigmatic element, is a shining example of that journey. It's a beacon guiding us toward a deeper understanding of matter energy and the fundamental forces that govern the universe.
This has been an incredible deep dive into the world of Oganesson. It's an element that sparks our imagination, challenges our assumptions, and leaves us with more questions than answers.
And those unanswered questions are precisely what will drive future research and lead to even more profound discoveries. Who knows what secrets Oganesson and other super heavy elements still hold?
Well, on that note, we encourage you to keep those minds curious. The world of science is full of wonder and discovery, and the journey is far from over. Until next time, keep diving deep.